Pleasant day to everyone. Today we're going to discuss part 4 of Module 5, subject CE3151. So in this lecture, we're going to discuss another method in solving the roots of nonlinear equations, which is the open method. So for open method, this is a method in which we base our solution on formulas that would require a single starting value of our unknown x, or just like for the previous methods, which are your under the bracketing methods, would require two starting values. But the difference is that it does not necessarily have to be a bracket of the root. So we could start at any value here. So as our computation progress, it may sometimes diverge, meaning it will be moving away from the actual or the true value of the unknown x, or the root of the value x. Okay? For open method, one advantage would be that it is faster to use than using bracketing method. Okay? Since as the values would diverge away, it would also be converging faster than our bracketing methods. So under open method, you have two types, which would include the second method and the Newton Raphson method. So in this lecture, we are going to focus first on the Newton Raphson method of determining the roots of nonlinear equations. For Newton Raphson method, or also simply known as Newton's method, this is a quick way to find a good approximation for the root of a real valued function f of x equal to 0. So the idea for Newton-Raphson method is that a continuous and differentiable function can be approximated by a straight line tangent to the graph of the equation. So given now the graph of the equation, using Newton-Raphson, we are going to identify the lines tangent to our graphs. And using these tangent values or tangent lines, we can now identify the true solution or the true value of your unknown. So in here, in this graph, we can see that for our first iteration, we could solve now for the root of our equation. So we have the derivative of xo, or our starting point, starting value, is equal to, ito yung slope niya. So slope is simply equal to y over x, in which it's equal now to the function of x sub o, which is y, minus 0 divided by x sub o minus x1. So arranging this, we could now solve for the value of x1, this value. Okay? And next, as we move on to our next iterations, we will now have the equation, the function or the derivative, the function of your ith iteration is equal to, as you can see, almost similar to the equation of your first iteration, except that for the function here, it's for the function of that value of x, or yung kung pang ilang iteration, function ng pang ilang iteration natin. Okay? This one. So arranging this, we could now define the formula that we will use for Newton-Raphson, which is equal now to xi plus 1 is equal to x sub I minus the ratio between the function of xi divided by the function of its derivative. Okay? So you just remember this equation. So for the continuous and differentiable equation or function fx equal to o, the following algorithm or procedure will be followed. So for step 1, we first choose an initial value, x sub o. and then find the function of its derivative or its derivative value. Next, step 2 is to compute the next estimate, which is x1 plus I, using the equation of Newton Raphson. Okay? And then step 3 is to calculate for the approximate percent relative error, EE, is x1 plus I minus xi divided by x1 plus I. So this is similar to the equation of our approximate error for bracketing method. So parang ito yung x new minus x old divided by x new. So it's almost the same. So once we have computed for your approximate error, then step 4, we stop our iteration if the approximate error now is less than our stopping criterion or stopping error. Okay? If it does not follow this condition, EA is less than ES, then we have to repeat our step 2 and step 3. So to consider, Newton Raphson method will also have its drawbacks or disadvantages. This would now include the tendency of our results in oscillating around the local maximum or minimum without converging to the actual root. So meaning, our results will be moving back and forth from a higher to a lower value, but it will not be meeting on the actual root. Okay? So another drawback is that for division by 0, it will when involved in Newton-Raphson formula, for the function or the derivative of the function, hindi natin pwedeng gamitin si Newton-Raphson. Okay? So this is a graph showing an example graph showing our drawbacks. So if you're going to solve for the first one, so nagkakaroon ka lang ng changes in the values but you are not meeting the exact point or the true value of our equation. So another drawback is that when the function of x oscillates and have several roots, you may choose an initial guess close to a root, but it will be jumping and converge to other roots in the process. Thus, since it's jumping near your initial guess and another root, then it will become oscillatory, which leads to an endless cycle of fluctuation between xi and xi plus 1 without convergence to our desired root. Okay? So this is another example of a graph of a function in which there will be oscillations in our computations. So we have this point, so it's converging or it is jumping back. It will be jumping back and forth and will not be able to meet. So you can see from the graph, it is not moving near our intended point. So it's moving near other roots. So that's one drawback of your Newton-Raphson method. Okay? So to understand Newton-Raphson method, let us solve an example. So for the given function x equal to 8e raised to negative x sine x minus 1, we determine now the first root of the unknown x, and we will use an initial guess x sub o equal to 0.3 and perform a computation up to 3 iterations. In this, since we are dealing with trigonometric functions, take note that you have to use the radian mode in computing for the value of x. So for our solution, for step 1, so we first determine the slope of the equation. That is by determining the first derivative of the equation f of x. So for this equation, The derivative now will be given as 8 e raised to negative x times cosine x minus sine x. So after computing for the slope of our equation, f prime of x, we move to step 2 to determine our first iteration using x sub o. So again, we determine first the function of the equation when x is equal to 0.3. So we'll have here 0.7514. And then for the slope, it is equal to 3.9104. Okay. Then we move to step 3. We compute now for x sub 1, or the value of x for the first iteration. So in computing for x sub 1, we use our formula for Newton Raphson, which is equal to x sub I minus f of x sub I divided by f prime of x sub I. So we were able to identify now the functions, the values of our functions when we substitute x sub o equal to 0.3. So this will now be equivalent to 0.3 x sub I minus its equivalent function 0.7514 divided by 3.9104. Simplifying, we have now x1 is equal to 0.1078. Then we move to step 4. Compute now for the approximate error, which is equal to 0.1078 minus 0.3 divided by 0.1078, which will give us 178.18%. So this is a very large number, meaning our error, or the value that we have computed for the first iteration x sub 1, is very far from the actual root of the equation, meaning we have to do another iteration. So for our solution, we could simplify or present our solution through a tabular form. We have for the first column your iteration I x sub. We have the function of x sub I. Then we have our derivative for the given equation, and by substituting now the value of xi in this equation. So we also have your x1 plus I, which is computed using our Raphson method, or Newton Raphson method. And then we have our approximate error. So we have computed already for our first iteration 1, I is 0. So x sub I, or x sub o, is 0.3. We're able to compute for the equation when x is equal to 0.3. So we have 0.7514. Then for the derivative, it's at 3.9104. So x1 is equal to 0.1078, and the approximate error is 170.29. So for our second iteration, we have I is equal to 1. So our xi now will become, so xi, or x1 is equal to 0.1078. So itong value na ito, lilipat lang dito. Then we substitute this value in our equation to arrive at negative 0.2270. Substitute xi in the equation of the derivative, so we'll arrive at 6.3680. And then with that, we can now compute for x1 plus I, which is now x2, or the second iteration for x, which is equal to x sub I minus fxi divided by f prime xi, which is equal to 0.1434. So computing for our approximate error, this value 0.1434 minus 0.1078 divided by x sub 2, 0.1434 will give us 24.18. So meaning we have moved closer to the root of the equation. Then with that, we can now move to the third iteration, which will have I equal to 2. So x sub 2, we have computed already, which is 0.1434. Substitute x sub I or x2 in the equation, we get negative 0.0095. Then substitute again x sub I in the derivative equation. So 5.8696. We can now compute for x sub 3, which is equal to 0.1434 minus negative 0.0095 divided by 5.8696, which is now equal to 0.1450. And with that, our approximate error now can be computed at 1.10. So we are only required to move until 3 iterations, so we could stop here already. So meaning, at the third iteration, the value of x now, or of the approximate root, is equal to 0.1450 with an approximate error of 1.10. Or, if the number of iterations is not given, then we could continue again with our iterations. So if we're going to continue with our iteration, we'll now have the fourth iteration with I is 3. So x3 now is this value, 0.1450. So substitute in the given equation, we now arrive at negative 0.0001. And then for the derivative, that's 5.8476. In computing for x4, which is 0.1450 minus negative 0.0001 divided by 5.8476 will arrive at 0.1450. So it's equal to this. Computing now for your approximate error, the new one minus the old one divided by the new one. So we have a 0% error, meaning even if we have not continued with the fourth iteration, the true root now of the equation 8e raised to negative x sine x minus 1 is equal to 0.14. Okay, so that's it for example 1. Let's solve another example. Determine the root of x squared minus 4x minus 7 by Newton Raphson method using an initial guess x sub o equal to 5. So for our solution, we could again present it in a tabular form. So we have iteration I, x sub I, the function of xi, the derivative x1 plus I, and your approximate error. So for function of x sub I, it's equal to the given equation x squared minus 4x minus 7. The derivative of the equation will simply be equivalent to 2x minus 4. And for our x1 plus I, that's equal to x sub I minus f of x sub I divided by its derivative. So our first iteration, I is equal to 0. So x sub o is 5. Substitute 5 in our equation, we now arrive at negative 2. So 2 times 5 minus 4 is equal to 6. So we'll now arrive for x sub 1 is equal to 5 minus negative 2 divided by 6, or that's 16 over 3, or a 5.333 value. So approximate error will now be equivalent to 5.333 minus 5 divided by 5.33, which is equal to 6.25. Okay? So no given number of iterations, so we just continue until we reach a low value of e sub e, or an e sub e equal to 0. Okay? So next we have second iteration. So we solve now for x sub 2 using x sub 1, which is 5.33. Substituting in our equation, we'll have 0.11 11.1. The derivative will arrive at 6.6667. So we have 5.33 minus 0.1111 divided by 6.667 will arrive at 5.3167. Computing for our approximate error, that's equal now to 0.31. Then, we move to the third iteration. So, yung x natin kaninang na-solve, yun na yung gagamitin nating x sub I. That's 5.3167. Substitute this in x squared minus 4x minus 7. So, we have 0.0003. Derivative is equal to 6.6333. So, we'll have 5.3167 minus 0.003 divided by 6.6333 will give us 5.3166, which is having an approximate error of 0.001. Okay, so we could stop here already since our approximate error is at 0.001. So we could assume it already is equal to 0. Or if you still want to prove that it is at 5.31662, you can still continue for the fourth iteration. So we'll have xi will be 3166. So xi now is 0. F prime is 6.633. So it's 5.3166. So it's really at, the root is really at 5.3166. Okay? So that's for Newton Raphson method. So I guess it's advisable to present our solutions in this manner so that we will have a systematic and orderly solution. Okay? So that's for the first method under open method, which is the new Raphson method. So thank you for listening. For the next lecture, we'll have the second method, which is the second method.